So this is the lab for the hypothesis testing for means. If you have not already done so, please look at page 95 through 101 and just try all the problems that you can do. You won't necessarily know what all the words are because some of them are new, and then also because some of them are worded a little differently here than how I word it. So I'm going to change some of them. But there's plenty in that section that you do know how to do. So if you haven't tried it yet, give it a try first and then come back to this video. But for those of you that have tried it, let's get started. So here is my screen. And we have page 95 here, and we're talking about the hypothesis testing for a population mean. So this first example here, right? Just tried to write on my screen with a ballpoint pen. That is clearly not going to work. All right, let's stop it. I had to take a quick break to go find my pen, but I found it. So we are here at the population for means, and this first example with the monarch's magnetic field. Again, if you have not stopped and read this, please do so now, because I'm not going to read through the words part of the example. I'm going to assume that you've already done that, but I'm just going to jump right in. And so here we have just a little bit about determining the hypothesis of review. So again, the null hypothesis is always equals. So in this example, or they're just kind of setting it up right here, they're using the letter K to represent some number. But you can see in the null hypothesis that mu equals K. And then for the alternative hypothesis, we have these three options: less than, greater than, or not equal to. And equally important, once you have chosen which alternative hypothesis you want, you also want to list what test you're using, left, right, or two-tailed. Okay, so here we have mu being the mean magnetic intensity for all monarch butterflies, so we don't need to state that. And we just want to go ahead and write out the null and alternative hypotheses. So the null, oops, go back to that, the null and the alternative, and we are in mean, so we are using mu. And in this problem, we are talking about, let's just go back to the words real quick. It says it must be shown that their mean magnetic intensity exceeds 200. And then this will come up in a little bit too, so I'll circle that. But it exceeds 200, so exceeds is greater than. So our alternative is greater than 200, and we're going to use the same number with an equal to sign for the null. And since I did that, well, here it has as the next question, is it left, right, or two-tailed? So normally I just write it like right over here, but since it asked it as a separate question, since it's greater than, this is going to be a right-tailed test. Okay, so here we have the data for 16 butterflies that were examined. And at this point, hopefully you have already put this into your calculator because you know how to do all of these calculations. But just as a reminder, this whole thing goes into L1 on the one variable stats, and then you just have a frequency of 1. You're just putting it all in one list, and that will give us a mean of 289.81, a standard deviation, and the clue here, sample. Remember, sample means those alphanumeric letters, so it's X bar and S. This is not mu, and this is not sigma. And it really matters right here because X bar is all the calculator will give you, but your calculator gives you S and sigma, so we want to make sure we're getting S, the 141.50. And then N, it told us already that N was 16. So if you did not get N is 16 in your calculator, that means you missed one of these numbers, or maybe you added too many. All right, next, is the sample mean consistent with the alternative hypothesis? So we have I'm just going to round that to 290. And our alternative hypothesis is greater than 200. So that is consistent with our alternative hypothesis. It's a nice check. That way, in case you get confused as to greater than or less than, you can just use that as a check. All right, is the sample, oh wait, I actually did that one already. Yes. Is the sample size large enough to satisfy the criteria for approximate normality? And that's going to be no, because n was 16, which is less than 30. So if it's less than 30, we cannot go ahead and approximate normality unless it tells us we can. And so looking at this, they actually did a histogram for us on the next page. And we can kind of see that. Oh, that was a bad version of it, but something along those lines. We can see that it's sort of bell-shaped, roughly normally distributed. So we can say probably. Whenever you're using roughly, we can't be so specific as to say yes, but we could say probably. It looks roughly bell-shaped. There we go. Okay, so looking at this, we are going to be using a test statistic. And so the test statistic, because we are using mean, because we are using the mu, just like we did in chapter 8, that means we're going to be using the t-table, and we're going to be, in this example, calculating a t for our test statistic. So means, which is mu, always goes with t. For later on, we won't do any in this video, but we will do it in the next one. For proportion, we use p, and that is going to be the z test statistic and the z critical value. But we are over here in mean for this example, so that's why we're using t. Okay, so it says we will use technology or tables, so we're going to be using tables, and I don't call it the p-value, I call it a critical value. So we're going to be using the table to find the critical value. And so just as a reminder from 9.1, if it was a left tail test, we would go here. In this case, we're writing down our t, and then we would have our reject region. On the left-hand side. And just before we get too far into this, as a reminder, we did these pictures in 9.1. So this is the same pictures that we talked about. Less than is the left-hand, less than is the left tail test. And so for a right tail test, which is this picture, kind of awkward spacing, but here we have a right tail test. And so our reject region is to the right. It's wherever the tail is, where that shading is, that's where our reject region is. So here we have it right here. And again, we're using T. And then finally, if we are using two-tail tests, it has two tails. One, I don't know if you saw that. I just clicked into something weird. But it should be back to normal. Okay, my hand kind of hits buttons sometimes. Here we have the reject region on both sides. So this would be our T, our critical value T, and then this over here would be negative T. And we'll talk about that when we use the table to come up with this. So this one would have two different possible reject regions, greater than and less than. Okay, so now we are going to calculate the test statistic using that formula up above, which was actually back a page. We're going to be using that formula right there. And looking at it, it kind of has like memories of central limit theorem and z-scores and all that. So yeah, it definitely is similar. However, there's mu's and x bars, so that's different to have them both mixed in the same problem. Okay, so we're going to calculate the test statistic. So T is, let me just write it here so we can see it while we're working, x bar minus mu over s times the square root of n. So we have x bar, that's the one we calculated, minus mu, I'll come back to that in a second, over s, which we calculated, that's a 5. And then over the square root of our n, which is 16. Okay, so x bar, s, and n came from our calculator right here. X bar, s, and n came from this number 2a. Mu, we actually got directly from the problem as the first thing we did. So right here, we wrote down that mu equals 200. And this is a very common mistake that people make. They have no idea where to find mu, and they don't realize that that was actually the first thing they wrote down was what mu equaled. So we're getting mu from the vocabulary in the problem, and we're setting it up as our null hypothesis. So coming back here, that's why I got a 200 right here as our mu from our null hypothesis. And you put all that into your calculator. Make sure you're practicing putting all of this into your calculator. So that way, you know you're doing the fractions right and the square roots right. We're going to get 2.54. So now it says to sketch, and then it says the area that represents the p-value. We're actually not doing that. We need to find from the table what number we're using. And so we're kind of doing all of this together. So I'm just going to draw a picture over here. This kind of represents all of these. And so I need to find, let me just cross that off, find critical value. So now to find the critical value, I'm going to go to the table. But before I do that, I need to know two things for T. I need to know the degrees of freedom. So that's going to be 16 minus 1 is the same degrees of freedom as before. And then I also need to know what alpha is. And that was something I circled a while ago. So let's go back to the problem again, back to the beginning. So our level of significance is alpha. So in this case, alpha is going to be 0.05 for 5%. Just as a quick reminder, when we were doing confidence intervals, we would say that a 95% confidence level, and then I did 1 minus alpha equals 0.95, and so alpha equaled 0.05. So they go together. 5% and 95% go together to make 100. So a problem you would see in chapter 8 that said a 95% confidence level will go along with a problem that you'll see in chapter 9 with a 5% level of significance. And so that is what we use for alpha. Now, alpha can change in the problem. It will tell you, or if it doesn't tell you, we'll use 0.05 if it doesn't tell you. That's the most common. I'll write that down when it comes up. Okay, but alpha is 0.05. And so I'm going to look at table. Go to table with the T's. And so looking here, I have area in 2 tails, area in 1 tail. And so since this is a right-tailed test, we are going to be using the area in 1 tail. And notice, I already wrote this from the other video, but I have alpha. Those numbers that are listed are alphas for 1 tail and for 2 tails. And so 0.05 is what we're using. We have a degrees of freedom of 15, And so our test statistic, our critical value is going to be 1.753. So this is the same table we used, chapter 8 down here at for the confidence level, 95%. And then up here, we're doing the area in one tail. And so here we have chapter 9 at the top. Same table, just different parts of the table. So again, 0.05 is our alpha, and we're going down to degrees of freedom of 15, 1.753. So I got, here's my table, or here's my picture. It is a right tail test. My critical value is 1.753. I just got it right there. And then now I want to put my test statistic on here. The test statistic is 2.54. This is a number line with 0 in the middle. So 2.54 would be over here on the left, and anything, on the right, and anything over here is in the reject region. All right, so what we want to do, it says, should we reject or fail to reject the null? It landed, we're going to reject the null because the test statistic landed in the reject region. And so what we have here is we have this line that we drew, the cutoff, which is we got from the table, our critical value. And then what we did was we said, on what side of the line is our test statistic? Reject region, or if it was on this side, it would have been fail to reject. However, that's not where it landed. It landed on the red, the reject region. So we will reject the null hypothesis because the test statistic landed in the reject region. And so what we want to do is now state a conclusion for this problem. And so what we're going to say, there is sufficient evidence to support the claim. I skipped B, that's why I was pausing for a second, because I just realized I skipped B. Okay, so since we reject the null, that means we are supporting the alternative. So there's sufficient evidence to support the claim, and the claim is the, so you're not going to write this right now, but if this was a test, you wouldn't write what I wrote in green, in red. You would just literally write the alternative, which is what we're going to do now. And the alternative is that we have, I forgot, it was greater than 200, but there were some units in there that I didn't write down. So there's the problem. Here it is. In order to, it must be shown that the mean, so our alternative is that the mean magnetic intensity exceeds 200 picoemos naturally. So going back, the mean, oh, I have this written tattoo. The mean magnetic intensity exceeds 200 picoemos. What? No. Okay, whatever. Naturally. Oh, there we go. So the part that is our alternative is, we said, just as a reminder, mu is greater than 200. So this is just the alternative, but inwards. And so that is our conclusion to that problem. So there is sufficient evidence. And so sometimes we would say there is not sufficient evidence to support the claim. And we'll get to that on other problems. But the problem will always end with whatever your alternative hypothesis is. All right, so let's go ahead and look at number 2. Or not number 2, but the second problem, the mean lifespan of batteries. And maybe now is a good time for you to pause the video now that you've seen a full problem worked out. And maybe you can do more on this problem than you were able to last time. So go ahead and pause the video and see if there's anything that you're able to fill in more than you already have. And we're back. Oops, maybe we're back. Here we are. And so we have, I'm going to give the null and alternative for this battery test. So we have our null. Ones aren't coming out right today. And our alternative. And in this problem, we are comparing mu. Well, first of all, this whole video is about mu, but I can see keywords in here that are telling me that it's definitely mu. And then we're comparing it to 55 hours. That's what the null is. The null is 55. And then the claim that we're testing is that the new battery is shorter than the brand they currently use. So that would be less than. Since it's less than, it is a left-tailed test. Okay, so in this example, we chose 40 batteries, so N is greater than, just write it out, N is equal to 40, which is greater than 30, so yes. If it's greater than 30, automatically works. If it's less than 30, then the distribution needs to be approximately normal in order for you to use this test. All right, is the sample mean consistent with the alternative hypothesis? So sample mean is 52, and that is the alternative, just to write them both together, is less than 55. And so yes, it is consistent with the alternative because 52 is less than 55. Doesn't give you the answer to the problem. It just tells you if you're on the right track. Okay, so we want to calculate the test statistic. So T is going to be X bar minus mu. So X bar was from here. S, okay, N is our 40. And then mu was 55 from our alternative, our null hypothesis. So we have X bar minus mu over S divided by the square root of 40. Put all that in your calculator and you get negative 190. All right, so then we are going to draw the picture. This is a left-tailed test. I know that what T is, but I don't know what my critical value is yet. So I need to figure that out first. So critical value. So from the table, or to get to the table, we are going to use the degrees of freedom of 39, one less than the sample size, and alpha. So let's go back to the problem. and it says we are testing at a 1% significance level. So alpha equals 1%. Now, just a little side note, 1% is 0.1, 10% is 0.1. It's like money. 1%, 1 penny. 10%, 1 dime. So just make sure you keep your decimals straight on that when you're working these problems out. And so alpha is 1%. I'm going to go to the table. We are using a new alpha. This is still one tail, so I'm still down here on the second line. I have my 1%, but then over here I have this new thing. It says for left tail, use negative one tail values. So I'm going to use the one tail value. I use the 0.01, and I'm going to go down to 39, which actually I'll end up at 40 because that's the closest. So 2.423. However, it says for left tail, use negative one tail values. So I'm going to write negative 2.423. This just saves us from having a whole bunch of different tables. So we can just use the same table and we get negative 2. Negative 2.423. And so we're trying to determine what side of the line our test statistic lies on. So our test statistic was negative 1.9. Here's our 0 in the middle, so negative 1.9 lies on the right side, and this side is our fail to reject. We shaded to the left. And so we have determined that we will fail to reject the null hypothesis. And so what we have determined is that we cannot support the null. We cannot support the alternative. So if we reject the null, like we did with the butterflies, then we support the alternative. If we fail to reject the null, then we cannot support the alternative. So instead of saying there is sufficient evidence, we're going to say there is not sufficient evidence to support the claim. And remember, this is where you're going to write claim, which is the alternative. And so the alternative was that the new battery is shorter. The new battery's lifespan. The average battery life for the new battery is shorter than the brand they currently use, or using the numbers here, shorter than 55 hours. All right, we'll just ignore that highlighting. I claim that the average battery life of the new battery, you can say shorter or less than. Say shorter than, and then I'll use the numbers from the hypothesis, 55 hours. I'm going to make sure you have the units on there as well. So this is the only difference between this conclusion and the last conclusion is that we were not able to reject the null. So if we fail to reject the null, then there is not sufficient evidence. So that's the difference. So the two ways to write the conclusion is either is sufficient evidence to support the alternative or there's not sufficient evidence to support the alternative. Okay, and we are not doing problems that have this, what type of error was made. So we're going to skip 11. Okay, last problem, and we've already done a right tail test and a left tail test. So I wanted to make sure that we did a two tail test as well. So again, if you have not done this problem, or if you just did part of it, but maybe now you have a better understanding, go ahead and pause the video and we'll be waiting for you when you come back. And we're back. So go ahead, and my husband's laughing at me making this video. Okay, so we have this problem where we have all of these amounts listed here of soda at random times throughout the day. I'm noticing this significance level. So I have alpha. I always forget to do that, so I'm trying to do that at the beginning now. And right here, the claim is usually the last one. But it says the mean amount of soda is different than 600. Different means not the same, not equal. It doesn't mean bigger, it doesn't mean smaller, it just means different. So this is why we're going to be getting into a two-tailed test. So for the hypothesis, the null is that the mean is equal to 600 because null is always equal. And the alternative is that the mean is not equal to 600. Like we said, this is a two-tailed test because it is not equal. So the sample size here is less than 30. It's 8. However, the population is normal. You can see that right here. So it's okay to use. So it's less than 30, but okay to proceed because the population is approximately normal. Okay, so plugging all of those into your calculator, we get X bar equals almost 600, 599.90, that's very close to 600, with a standard deviation of 0.126. And as we said above, the sample size is 8. The sample mean consistent with the alternative? Well, it's very close to 600, but it is not equal to 600. So yes, our sample mean 599.98 is different than 600, which is what the alternative says. Okay, so we're going to calculate the test statistic. So much space, a little bit of space here. So T is X bar minus mu over S over the square root of 8. If you are not getting these fractions in your calculator to work out, then just come to my office hours any Monday from 9 to 11, or you can email me a different time and we can meet up over Zoom and we can talk about your calculator. Because as you've seen, you need to be able to get this number in order to finish the problem. Okay, so we are going to draw a picture. Anytime it says p-value, we're doing the critical value. And this was two-tailed, so I'm going to shade it on both sides. We said earlier that alpha is 0.01, and the degrees of freedom, sample size -1, so 8 minus 1 is 7. So now that we go to the table, we're going to be focusing on the top. So we did right tail, we did left tail, and those differences. And so now we're going to be doing the top because the top is the area in two tails. And so for this problem, we have our alpha is, what did I say it was? I think I wrote that wrong. that's the old problem. Alpha is 5% in this problem. Yes, alpha is 0.05. So we have 0.05 is our alpha. Again, that one's very common. You'll see that a lot. Our alpha is 0.05. And that's right here in the middle. I know there's extra zero. Don't worry about that. 0.05. And the degrees of freedom was 7. So we're going to get 2.365. And what that's going to do is that's going to give us our number on both sides. And we're going to kind of use that left tail rule where we're going to make it minus as well. So this is actually going to be plus or minus 2.365. Because on our picture, we have these 0 in the middle. So this side would be positive 2.365. And this side over here would be negative 2.365. So you can get both numbers at once, the positive on the right and the negative on the left. This problem, however, we have that tiny little negative 0.45, so that's going to be right in the middle. And anything in the middle is fail to reject. If you're having problems remembering any of these, just go back to the 9.1 notes. And we have all these pictures here. So the bottom picture is what we're talking about, the not equal. The fail to reject is in the middle, and the two reject regions are on the outside. So we are going to fail to reject the null based off of that picture. So if we cannot reject the null, then we cannot support the alternative. So we can write our conclusion to this problem that says, since we're not supporting it, we'll say there is not sufficient evidence to support the claim. Back to the problem, we know the claim was not equal, and so here we have the claim is that the mean amount of soda is different than 600 milliliters. Of soda dispersed is different than 600 milliliters. So what we did was we said there was not, because we can't support the claim, so there was not sufficient evidence. And then everything after the word claim, all of that is the alternative hypothesis. So in symbols, the alternative hypothesis was mu is not equal to 600. And as a sentence, we just write it as the mean, mean amount of soda is different, not equal, than 600. And we have the units in there for milliliters. All right, so that is everything for hypothesis testing with means. And next time we'll be talking about hypothesis testing with proportions.